Hello. Let's talk about boats. How did they work? So, how boats float. So maybe a study of floating in general. I call floating when something is on the surface of a fluid. That fluid could be air. Something could float to the top of the atmosphere. That fluid could be water or some other substance. Let's say it's water, something floating like a typical boat. There are two forces acting on this boat. This is just a crate, a box, but let's call it a boat. There is a submerged volume, which is different from the total volume. The submerged volume causes a buoyancy force, and the total volume and the mass causes gravity. When something is floating, those are equal. Why? Because it's not moving. And F net therefore is 0. So this is not the case of rising. Like if I were to put something low density, density less than density of water, like a air bubble or something underwater, buoyancy force will be bigger than gravity until it goes to the surface, and then there will be less submerged. So buoyancy force will then match gravity. Notice here my arrow is bigger for buoyancy force because more is submerged. When you have more submerged, you have more buoyancy force because you have more of those pressure forces pushing, more V sub. So this brings us to Archimedes' principle. Buoyancy force, we need to correct, is V submerged G, where density times volume is the submerged mass of the displaced fluid. Some of you got that when we did buoyancy derivation in class. What is this? Well, this is the density of the fluid times the volume that is being displaced. So it's the mass of the water that is displaced, as if there were water there. There's not water there, but if there were water here, right, this is the submerged volume, the displaced volume. What's fascinating is the weight of the water that's being displaced is the buoyancy force. The buoyancy force is the weight of the displaced fluid. Weight as in force of gravity, it's mg. This is called Archimedes' principle. It was not his eureka moment, but it could be considered that. This is called Archimedes' principle. So when you have a boat floating, again, pause the video if you want to take that in, go back a step. If you have anything floating, the submerged volume is always less than the total volume. V total is both the areas, both of the volumes, meaning the shaded and the all of the above, right? V total is everything. This, right, mass is density of the object times V total. So when we have FB equaling mg, because it's not moving, we can easily see that the density of the fluid times the submerged volume times G, the weight of the displaced fluid, so this is the displaced volume, that's what's holding up the boat. This is holding up the boat. And countering mg. That's the concept of how boats work. that for boats to work, they have to displace volume underneath. And in fact, if you're ever in the bottom of a boat, you're under the water, or the water level is above you. It's kind of trippy to be in a boat and be in that low part, a little hull of the boat. So boats work by having hulls that are filled with air. So you still have low density, but you want them to be big volume. Right? That's going to equal density of the object times the total volume times g. So notice this is different than sinking or rising, because we have a different submerged volume than total volume. So I'm going to rewrite it here. Here only g cancels, and I get that the submerged volume, I'm going to divide by v total, bring that down. I'm going to then divide by FL, density of the object over density of the fluid. We now get a nice relationship for, say the density of the object is 50% that of water. So it's 500 kilograms per cubic meter. It's 0.5 times density of H2O. Well, if I plug that in there, and my fluid is water, I get that V submerged is 50% of the total volume. So if it's 50% is dense, it's 50% submerged. If it's 20% is dense, it's 20% submerged. If it's 1% is dense, it's 1% submerged. So if I have something that has a density of 10 kilograms per cubic meter, compared to a density of water, which is 1,000 kilograms per cubic meter. This is a little bit bigger than water. I'm sorry, a little bit bigger than air. Maybe this is like a bottle, right? Say I have a bottle that has this density. Then, right, then what's going to happen is the submerged volume will be barely under the surface, and it'll be 1% of total volume. I wrote total twice, but you get the point. Isn't that cool? The ratio of the densities is the same as the ratio of the volumes. And it's that displaced volume. Even that bottle has a little bit of submerged volume to hold it up. What holds up a boat? Displaced volume. What holds up a boat? The weight of the displaced fluid holds up a boat. How boats float? I'm saying that with my words. Feel free to write that down. Displaced volume, maybe I'll write it down. Holds this. Holds up a boat. The displaced volume. Archimedes principle, the weight of the displaced fluid is what's holding up a boat. So let's do another question. I came up with another bottle that I have maybe some stuff in. Say I have a liter bottle or a liter object, whatever it is, that has a mass of 100 grams. What is the submerged volume? What is the buoyancy force? These are easy questions. Here's what you do. First of all, you draw a picture. You draw the submerged volume. V sub, V total is 1 liter. By the way, whenever I give V, it's implied V total. So be careful. V total is 1 liter. So what is the submerged volume? Well, I could do this a few ways. Here's how you always want to do it. Be careful. Don't go to this one. I know I circled it, but really you want to go to this one. So I would circle that one. This is the most important one. So the point is, you draw a force diagram. You follow the 1, 2, 3 steps, 1, 2, 3, right? Draw forces, right? And then F equals ma, right? And then which is bigger? If floating, equal. They're equal because A is 0. So mg equals FB. So M is 100, 0.1 kilograms. Careful. Careful. 0.1 kilograms. Oh no. Units. And what's this one? This one is 0.001 or 10 to the negative 3 cubic meters. Please remember that, right? So if I have a 100-gram object that has a volume of a liter, 0.1 times 9.8 is gravity. That's going to be 0.98 newtons is mg. That's going to equal FB, which is the density of water, times the submerged volume, not the total volume, times G 9.8, like that. So 0.98 equals this. I could obviously cancel the 9.8s, right? But the point is FB also equals 9.8. So that answers that question. Or 0.98 newtons to match gravity. So we've already answered that. That's why I did that. Because mg is 0.98, FB therefore matches it. This is where you want to start every single time. Draw the forces, which is bigger, right? Which is bigger? Well, if floating, they're equal. Right? That's how we want to do it. Right, let me see if I can do this one with the forces. That looks good enough. So I can then solve for V sub by saying V sub equals 0.1 over 1,000, which is 0.0000. Right, that's 10 to the negative 4 cubic meters. Right, which is a tenth of a liter, or 0.1 liters, because I multiply by 1,000 to get liters, and that's going to be 100 milliliters, however you want to write it, just like that. What's a shortcut? It's a shortcut, right? If on the verge of sinking, right, V submerged equals V total. Because as I add mass, right, if mg increases, then FB has to increase. If mg increases, it just increases. I'm writing up as increases. Maybe I'll use a different shorthand for that. If mg increases, I'll write it out. FB increases, which means V sub had to increase. This is the chain of logic. But what happens really? What happens is if you add mass, this vector gets bigger, but FB is the same. So it goes down. So I have a net force down, which increases V sub, which increases my eraser erased my box there. If I add mass, mg increases, which increases the F net. So if I add mass, 1, mg increases. So F net is down. So V sub increases. So FB increases to match mg again until the F net is 0 again, equalizes. Right? This is kind of like the loose logic. This is loose. This is more grounded. Let me put that in fuchsia. What is that, magenta? I like it. This is grounded logic. So V sub increases when you add mass due to this, because it's pushing down. Mg increases down. right? Of course it does. If I add more mass, what's going to happen? It's going to push it down more. It's going to weigh it down, of course. That down arrow increases. This should make tons of sense once you think about it. Like, okay, that makes sense. This is like from the equation. This is the math logic. I call it loose logic because it's not really cause and effect logic. It's like, this is what the math says. If mg increases, then fb increases, and v sub increases because I know mg equals fb ultimately. But this is the mechanism. Right? This pushes down, which increases v sub, and v sub, of course, increases by Archimedes principle, increases the buoyancy force because there's more pressure forces, right? So v sub increases, so more FP forces, FP. And remember, the FP forces are FB. The buoyancy force is the pressure forces. So there's more water, right? More water pushing on the object. So there's more water pushing on it. So the buoyancy force increases to match mg, finally equalizes, and it stops and it rests at a new v sub. On the verge of sinking, though, v sub will equal v total. So on the verge of sinking, so the maximum cargo something can hold is this. It's when v sub equals v total, right? And it's when the density of the object equals the density of water or the fluid. It's when it's neutrally buoyant. But here's how I do it. I would say, okay, the object is now barely under the surface of the water. V sub equals V total, such that if I added 1 more gram, it would sink. Max cargo, still floating. FB still equals mg, right? So if I wanted to say, okay, example, I still have my volume equals 1 liter bottle. What's the maximum mass it can have before sinking? Well, the maximum mass it can have before sinking is when FB equals mg and V sub equals V total. Because then it looks like this. So draw a picture, it looks like this. So I have FB being 1,000 times V sub, which is now 1 liter, 0.001 times G equals mg, and I'll cancel that, and I get mass equals 1 kilogram. Why does that make sense? Because the density of water is 1 kilogram per 1 liter. Right? So the density thing becomes like an afterthought. It could be a way you solve it, but I really want to emphasize solving it via forces, because that's what's really happening. Where if I get a V submerged of 1 volume, I'm going to be able to hold up to 1 kilogram. Now let's look at this from one other angle. Back to like when the mass was 100 grams and we had 10% submerged. Right? We had, what was it, 100 milliliters submerged? Right? 10% submerged because 100 grams, 0.1 kilograms per 1 liter, right, is 0.1 kilograms per liter, which is 10% density of H2O. That's 10%. Sorry for the sloppiness. Hope that makes sense. If I wanted to convert to kilograms per cubic meter, that is 100 kilograms per cubic meter, because I just multiply by 1,000 to convert from liters to cubic meter because it's in the denominator. That's 10% of density of H2O, so 10% is submerged. I'm going to write that a little more clearly. 10% of density H2O. V sub was 100 milliliters. Mass is 100 grams. What's the connection there? Remember, mg equals FB equals the weight of the displaced fluid. So if holding 100 grams, you need V sub, the displaced fluid, to be 100 milliliters, because that's the density of water. I hope that made sense. But the point is, the weight of the displaced fluid will always match gravity if you're floating. So this is floating. So this is the shortcut. Right? If you're holding 100 grams or 0.1 kilograms, you need a displaced weight of, displaced 0.1 liters. Because 0.1 kilograms translates to 0.1 liters if we're in water. I don't know if that made any sense. I hope it did, but that's the shortcut, right? If I have 100 grams, that means 100 milliliters is submerged. If I have 5 kilograms, that means 5 liters is submerged, because the weight of the displaced fluid will always match gravity. That's how boats work. Volume holds them up, and the heavier they are, the more they sink in. And the weight of the displaced fluid will always cancel their gravity.